One of the great unexplored areas of biology is looking at how different organisms solve problems in their environment and then connecting that in some way to a more reductionist view or a cellular view of how that is represented on a lower level. So one thing I'd like to talk about is novel smell detection in Drosophila. And these days in Pittsburgh, where I live, it's currently April, and we have a bloom of these famous Bradford pear trees. And there's a natural question in terms of what we're going to talk about is this sensation that I'm getting currently new? Could be a sight or a sound, or it could be a taste. I mean, it's the same sort of question that database search algorithms ask. Is this image of a tree, for example, is it already contained in a database? With respect to smell, though, our brains can be fooled. I showed this image of a Bradford pear because some people think that they smell like rotting fish, other people think that they smell like wet dog, and so forth. And so they do seem to be familiar, and there's no infinitude of different smells that we can detect. So this is an instance of a much more general type of question, which is if I have a database or a set of objects S and some other object X, have I seen it before, yes or no? And that's a very, very simple problem to state. You might say it's, in theory, pretty simple to solve, too. All we have to do is range through all the elements of S, and if our input object X matches any object in X, we return S, or return any object in the data set, we return yes. Otherwise, we return no. So if we survive checking every element of S, then we know it's not in the set, and we can return no. The problem is that we know that this is not how our brains work. Memories can fade over time, and we have to make faster decisions when we explore our environment. S can be large to store, and we can't, in a split second, if we're in the jungle and we think, is that a tiger? We haven't evolved to sit there and think about it for 30 minutes. So we need to make a lightning-fast, heuristic-based decision in terms of identifying whether or not some object that we're sensing is in fact novel. One way that you could very quickly come up with a way of maybe not with 100% certainty, but with a good precision, determine whether or not your object is new, is to use a data structure called a Bloom filter, which is an array of sorts of zeros and ones, or bits. And the length is longer than the length of S, and so we're going to heuristically determine whether or not this new object X is already in the set, and I'll show how. So along with the Bloom filter, we're going to have K hash functions. We're going to show an example here with K equal to 3, and each hash function assigns an element of our set, or an object, to an integer between 1 and m. For example, if we look at a given smell, then what we will do is, after we hash that object for each of the hash functions, if the hash function assigns the object to I, we're going to set the ith value of that array equal to 0, if it's not already 0. So for example, if we smell a wet dog, okay, and that, or that object, wet dog, for example, is hashed by the three functions to the values 8, 1, and 6, then we set the Bloom filter array values corresponding to 1, 6, and 8 equal to 0. Now, what happens when we smell something new? Okay, then we would say if the first hash function of fish is equal to 4, well, this was set equal to 1, so we set it equal to 0. Maybe the second hash function of fish is equal to 3. That was 1, so we set it equal to 0. But the third hash function is going to be set equal to 1, and that value was already 0 from our wet dog. And so, as a result of this, we could ask, how did we know that fish was a new smell? You might think about that for a second. The reason why it's new is because one of the hash functions mapped to a value that was equal to 1 in the hash table. Now, the question becomes, what happens if I give you 1/3 smell? So this third smell is Bradford pear, and it maps to the values 6, 4, and 3 as the result of the hash functions. You will notice that each of those values are all already 0. And so we would be tempted to conclude that we've already smelled that smell. None of those values were set equal to 1. And that's not right in this case. So if this were our heuristic, this bloom filter approach, which is lightning fast, we only have to consult our k-hash functions against the known bloom filter, then we would be fooled. And what we have just danced around is actually a theorem that says if you hash the object x and it maps to any bloom filter values that are equal to 1, then we can conclude that x is not in the set. Otherwise, we already would have set that value to 0. But if x maps to all values that are 0, we can't conclude that we've already seen x. We can just say that it's possibly already in S. And so we're not 100% sure on that side if we see all values equal to 0. So in practice, we would hope that we would use a large array to avoid that possibility, but it's always a possibility. The question is, how does this relate to Drosophila or fruit flies? So researchers have found that in the olfactory system of the fly, you have 50 neurons that can detect smells. And these olfactory neurons are connected to what are called Kenyan cells. So there's 2,000 of the Kenyan cells. And these connections are somewhat haphazard, seemingly random. There's no clear correlation between them. And the connections themselves are sparse as well. So a Kenyan cell is only going to be connected to about 6 olfactory neurons. So 6 times 2,000 means that there are about 12,000 connections that we have here. And once a smell occurs, it activates some subset of those 50 olfactory neurons. And a Kenyan cell is going to be excited if enough of those approximately 6 incoming neurons get excited. So if all 6 of the incoming neurons are excited, then we're probably going to have that Kenyan cell be activated. But if only 0 or 1 are excited, then maybe perhaps not. So as a result of this, you have 2,000 Kenyan cells, and the smell will cause some of them to be excited. In practice, one smell may excite only about 5% of those cells, but there's 2,000 of them, so a smell will activate about 100 of those Kenyan cells. Those Kenyan cells are in turn then connected to what are called mushroom body output neurons, or MBONs. And for people who have seen neural networks, they might get excited and say, this seems like a neural network, because it's a real neural network with a hidden layer of Kenyan cells, but that occurs in actuality in the fruit fly. So each of these mushroom body output neurons, and there's only 34 of them, will have in degree about 400. So they're connected to about 400 KCs. And that means that because only about 5% for a given smell, only about 5% of the Kenyan cells were activated, each MBON, you can think of it as getting an on message from about 5% of the KCs that it's connected to, and 5% of 400 is 20. So these are just some example numbers. The point is that the MBONs are storing or aggregating the inputs from the about 400 cells that they're connected to, and these signals can be represented or modeled as a bloom filter of length about 400. And if we have a new fly that's never smelled anything, that MBON is initialized with all values equal to 1. And a lot of work has gone into showing that this is an appropriate model for how the MBONs aggregate information. And then what happens if we get an on signal from the ith incoming Kenyan cell? Well, we set the weight of I equal to its current weight times delta for some small value of delta. So if it's 0.2, for example, that will lower it very close to 0, not all the way. And then we say, well, if the incoming KC is off, so if it's not activated, which will happen for most of those KCs, then we're going to set the weight equal to the minimum of 1 and the current weight plus epsilon for some small value of epsilon. So the idea of this being, we allow memories to sort of float back up towards 1. If we're not getting a lot of activation there at that point, then over time the memories will increase by epsilon until they hit 1 as a threshold. So as more and more odors come in, these weights of these synapses at the coming in from the Kenyan cells for each MBON are going to go up and down over time. And so you might think, for this model, what would a newish odor represent in terms of this Bloom filter model? And a newish odor would be one that, when it excites the Kenyan cells and those get passed on to this MBON, it would be one that corresponds to higher synapse weights or higher Bloom filter values. And so we have a quantitative way of measuring, in terms of these neurons, how novel the fly thinks that this smell is. So we can, in a sense, measure a confidence that a smell is new by say, taking the average there. So if we had 0.7, 0.9, and 0.5, we'd average them and get 0.7, and that's closer to 1 than it is to 0, so we might think that this smell is newish. So this is a short lecture that's taken and inspired by this paper that was in the Proceedings of the National Academy of Sciences, and special thanks to Saketna Navlaka, who I first saw discuss this paper and was one of the co-authors. It's a lovely model here because, for 3 reasons. Well, you have a memory of old smells, so those plus epsilons allow the old smells to sort of drift back to 1. You have continuous weights in 0 or 1. So we had a cool idea based off of Bloom filters, but we had only binary 0 or 1 values. And these continuous weights allow us to have more information. So is something brand new or something similar to what we've seen before based off of, say, taking that average of whatever your corresponding weights were for a given smell. But what's really interesting about this is that the traditional Bloom filter is this nice, fast heuristic for novel query detection. And this approach outperforms this traditional Bloom filter, as well as some other approaches. So it offers us an amazing example of an algorithm that's been developed by a fruit fly as the result of evolution that can also beat approaches that have been devised by humans to heuristically solve this problem as well. That's all I have time for. Thank you for joining me.